application with the class C, D, and E power amplifiers. This constitutes the chapter 9 of John V. Hagen. Now, where we are using these class C, D, and E amplifiers, we probably use them in the transmitters for amplitude modulation and FM modulation to achieve higher efficiencies. So you see, it's all about the high efficiency. Why we need these class C, D, E amplifiers. We don't use them for the audio applications because of a large distortion, and that distortion is due to the lower conduction angle as opposed to class A and class AB amplifiers. So they are used in cell phone transmitters where high efficiency increases the battery life. So that's one. It can be used as a large transmitters. So industries can use them in, for example, industrial heating, where they can save the cost of the cooling equipment and the bill. So it's all about the high efficiency, not about the fidelity, because they are nonlinear amplifiers. So what do we mean by the nonlinear is that the output signal amplitude is not proportional to the input signal. So hence they are unsuitable for high fidelity audio applications where class A or class AB amplifiers are preferred choices. So if you recall that for a typical push-pull amplifier configuration that we studied in chapter 3, for example, if you have a complementary pair of an NPN and a PNP transistor like this, so let's see, we have an input signal, okay, over here, and let's join this. So let's say this is let's take the load from the emitters of both NPN and PNP transistors. This is RL, okay, this is RL, and you see, since the output is taken from the emitter sides of both NPN, this is NPN is Q1, okay, and we have PNP, let's call this Q2, okay. So we have two transistors. It's a symmetric circuit. Why? Because both are in common collector configurations, okay. So we have, let's say this is plus VCC, okay, this is plus VCC, and this voltage is minus VCC, okay. So what goes on over here is, so once you connect a supply over here, an input supply, okay, it's like this sinusoidal input supply. During the positive cycle, Q1 conducts, so Q1 is on, Q1 is on during the positive half cycle. During the negative half cycle, Q2 is on, okay. So during the negative, this is for the half cycle, positive half cycle. It's like this, okay. Not for the negative half cycle. Q1 is off while Q2 is turned on, okay. So this is on for the negative half cycle. Q2 is on for the negative half cycle. That's how this class AB amplifiers and class B amplifier. So this is on for negative half cycles. All right. So that's how they produce an output. So for example, if this is an input, okay. So when the positive cycle comes, this conducts. This part conducts. Q1 conducts, since the PN junction is forward biased over here, okay. So Q1 is conducting. Q1 conducts, and it pushes the current in the positive half cycle through the load RL. In the negative half cycle, this transistor is off while this transistor is on. So for example, this is the negative half cycle. So in the negative half cycle, you see this is P, this is N, this is complementary pair, P and P. So this Q2 is on, so Q2 becomes on, and it pulls the current. It pulls the current from the load, and then it. So that's how it is. It turns itself on. So at the output V out, you have an output that is replicating the input, apart from the crossover distortion, which happens, which is the time taken for the PN junction of the transistor to turn on. But these can be taken care of by either you can use diodes over here, or you can have batteries. Okay, so if you use two diode pairs, for example, over here, you have a two diode pair over here like this, and you have another diode pair like this. All right. So you can remove these crossover distortions. So therefore the transistor is like a class AB amplifier, and what you have in a class AB amplifier is a smooth output, right? Almost a smooth output. So these transistors have a maximum efficiency of 78.5%, as you've seen before. Under maximum signal conditions, you can achieve a maximum efficiency of 78.5%. Okay, so you see the output is again a replica of the input. Well, nothing such happens in the class C amplifier. In class C amplifiers, okay, for example over here, Q1 was on in the first half cycle, Q2 was on in the negative half cycle. Okay, so this trend continues. Q1 is on, then again Q1 is on, then Q2 becomes on. So that's how you're producing the output, which is a replica of the input. But what happens in, for example, in class C for such input, you can have an output for which the conduction angle is even less than the half cycle. For example, it could be 90 degrees, okay, or even less. So nothing over here. Then again, for a positive half cycle, you again have something like this. Okay, so the conduction angle is small. So conduction angle is small. It could be less than 90 degrees. It could be 60 degrees. So why we have this is because in order to have an efficiency for class C amplifiers, you will see you can achieve an efficiency of 90%, theoretical efficiency of 90%, which is even greater than class A or class AB amplifiers. But again, you see that for such a waveform, which is a distorted waveform as compared to the input, you cannot use them for audio applications. Okay, they're used for example in transmitters, in cellular transmitters, where the efficiency is desired to save the battery life, for example. So in class C amplifiers, as opposed to class A, this is class AB amplifier, as opposed to class A or class AB amplifiers. This is class AB amplifier. So in class C amplifiers, the output sine wave amplitude is not a linear function of the input signal amplitude. Okay, so we cannot use them for audio applications. So, but again, the output power and the output sinusoid amplitude is again proportional to the power supply voltage. So you see, if you vary this power supply voltage, you can still get an amplitude modulated wave. So these amplifiers can be amplitude modulated by varying the supply voltage. All right, or they can be frequency modulated if you vary the drive frequency. Okay, and that is restricted by the LC part of the circuit. Well, where is this LC part? You see another difference between class AB and class AB or class A amplifiers, and difference between those amplifiers with class C amplifiers, that normally you have an LC tank circuit, okay, that is resonating at a certain frequency. Okay, so this frequency is 1 over this resonant frequency is 1, or you can show this is 1 over 2 pi under root LC, and you can by the combination of those LC components, you can select the quality factor of the resonant tank circuit. So you have an LC circuit, then you have a switching element, an active element. This is a junction field effect transistor. You can have a BJT, for example, or a vacuum tube. So a class C amplifier has a supply voltage, let's call this VDC. It has a LC resonant tank circuit, okay, which resonates at a certain frequency described by the LC elements of the circuit. It has a load resistance R, which could represent the radiation resistance of an antenna. Okay, it's a load resistance, and then an active element. So they consist of power supply, at least one switching element like a JFET over here, and then an LCR circuit. The R is the load. So often the radiation resistance of an antenna equivalent to a resistor. The LC network is resonant at the operating frequency, and it supplies a flywheel effect. You see, the flywheel effect means that, okay, if there is a stimulus over here like this, if there is a stimulus like this, there is a cycle on which it is on, and then if you're looking at the transistor as a switching element, okay, if this is a switch, then this switch is on when there is a stimulus, so it is on in this part of the cycle. It is off like here. It's off. So what happens is when we remove the stimulus, the LC tank circuit tends to give an output, V out, and if the output is sinusoid, then when the stimulus is removed, this sinusoid continues, and this is called the electronic momentum. So even without stimulus, you are still producing for a very large Q or a very high Q. If the loss is low, you're still producing a complete sine wave. Okay, so that's your flywheel effect. If there was no stimulant, or if it's not a very high Q circuit, the output will be like this. Okay, then it switches off. There's nothing over here. So again, when the stimulus is there, okay, when you're supplying the voltage at the gate, it's like this. So you don't have anything at the output when the switch is off, if you're considering this JFET as a switch. But a flywheel effect tends to, if for a very high QLC resonant tank circuit, it pushes the voltage to produce a full sinusoidal output voltage. All right, that's called the flywheel effect, or the electronic momentum. Now, this is your typical class C circuit having a switching element. So you're using this as a switch, which is shown over here. The switch is your JFET over here. This is the stimulus that you are applying at the input. Okay. So for a certain duty cycle, you have your stimulus is on, stimulus is there, then there is no stimulus. So on, off. Okay. And this switching is occurring at the rate of whatever is the width of this pulse. So you have an LCR circuit over here connected by the supply VDC, okay, and you owing to this flywheel effect for a very high Q LCR circuit. Assume that the Q is large. Well, normally in practice, there's always, for example, for LC, there's loss, so there is damping. For example, there's a dielectric loss in C, and then there is a resistor. This is coil. Okay, so there will be damping, and this damping this R is also going to contribute in damping. So, for example, a flywheel typically will be something like this, decreasing amplitudes like this. It goes on like this. So if you have a very high Q circuit, this damping will be low. Okay, this damping will be low. The circuit will be underdamped. Now for the analysis, for the purpose of analysis, we assume that there's the loss in LC elements is small. We have a high Q or very high energy storage due to the interaction between L and C elements, and we have a flywheel effect that produces a smooth sinusoidal output voltage like this. Okay, so that's your owing to flywheel effect, we have a complete sinusoid at the supply voltage VDC. Okay, that's the battery supply voltage, and then you have a maximum peak voltage of alpha VDC. Okay, you have alpha VDC. So you have a sinusoid which has an amplitude of alpha VDC and minus alpha VDC. Okay, with VDC. So this is clamped at VDC, and then when the switch closes, depending on whatever the cycle is at that instant in time, this current, the amplitude of this current will be equal to VDC minus, or so over here, and we are looking at over here. So this is the voltage. This is the voltage. VDC minus alpha VDC. Okay, alpha VDC divided by R, small r. So this R over here is the JFET resistance, switching resistance, because once the JFET is turned on, there is the capacitor charges, and this charge incurs some loss. This loss occurs due to this the finite resistance, small r. If it is open, then R is infinite. Okay, there is no current. But at the time when the R is when the switch is closed, then you have a small resistance onto which there is a current I, okay, over here, and this current is present when the switch is closed. So you have this much of conduction angle. Okay, it's not there for 360 degrees for a certain conduction angle, and this is whatever the voltage over here divided by the VDC minus alpha VDC divided by R is the current. Okay, so this is an operation of class C amplifier where you have the inactive device. It could be a transistor, BJT, FET, okay, or MOSFET, or a vacuum tube. So it's used as a continuously It's not used as a continuously variable switch, as a variable resistor, but it's used as a switch in a saturation region where you have a where the channel width is not that small. So so it's the JFET is a good conductor, okay, for just like an ideal closed switch. So the current is passing down the channel without much resistance, right? There's a small resistance R, which is much smaller than your load resistance, capital R. All right. So we're considering the JFET as a switch. All right. So to simplify the analysis, we consider the switch to have a constant on resistance R and an infinite off resistance, just like a power JFET model. So the switch is closed for less than half of the RF cycle, as you can see over here, right? During which time the power supply essentially tops off the capacitor, charges this capacitor up, and restores the energy the load has drained from this resonant circuit. So since the load is draining the energy, when the switch is on, there's a stimulus and the capacitor charges up. Okay, capacitor charges up maximum to a value of VDC plus alpha VDC. It is clamped at VDC, and then when the switch is off, then due into the flywheel effect, this sinusoid trend continues. Okay, and the current when the switch is on is VDC, whatever the voltage is over here, divided by the small resistance R, gives you the current through the JFET. Okay, and this I square R is the power lost during the capacitor charging. Okay, this I square R, this I square, the current flowing through the switch when the switch is on, I square R is the power lost in the JFET. So this is power lost in the JFET. Okay. So the switch has an internal resistance. Okay, so there is loss. So in recharging the capacitor, we lose some energy, which is given by I square over R. Okay, where I is this term over here, this term. Normally, LC circuit has a very high Q. We assume it's a very high Q circuit with low loss, at least phi. So its flywheel action minimizes the distortion of the sine wave. So it's almost a sine wave. So this distortion is caused by the abrupt pull down of the switch and by damping, and the other factor is the damping caused by the load. So we assume that there is not much damping, and this sinusoid continues at this constant amplitude. Amplitude is alpha VDC. Okay, alpha VDC. So Class C amplifiers are normally run in saturation mode, meaning that the switch, when on, always has its lowest possible resistance, so ideally much less than the load resistance. So R is much less than the load resistance, RL. If you remember for this JFET, the IV characteristics, they look like a BJT. So in the saturation region, when VGS is 0, the gate to source voltage is 0, you have the maximum drain current. And in this region, it doesn't matter what VDS is. Okay, it has a very small dependence on VDS. But for increasing VGS, it has a large dependence on VGS, because if you're going to increase VGS, okay, you're going to narrow down the channel width. Okay, so the current decreases. So for increasing VGS, you see, for VGS is negative. Just keep that in mind. So if you are going to increase VGS, you're going to decrease the channel width, and decreasing the channel width has an effect that IDS, drain to source current, decreases. That's how the characteristics are for the JFET. Okay, so there comes a pinch of voltage. Well, as you increase the VGS, the pinch of voltage is reached before as compared to VDS, because you're increasing VDS. So for example, in here in ohmic region or linear region, as you are increasing VDS, the current increases. The current is increasing in these regions. All right, but increasing VGS, the pinch of voltage is reached before. So over here you see, as VGS is, you keep on increasing VGS. Okay, you make the switch turn off. Okay, so the channel is the depletion width is so large, the channel width is so small, the current is negligible, and this is known as the cutoff region. This is cutoff region. Okay, so VGS is less than V pinch off. There is no current. The current is 0 over here. The current is 0 over here, right? So we are operating this JFET in the saturation region. Okay, when there is a small resistance and JFET is a good conductor, just like this condition is a closed switch. So over here the switch is closed, right? Switch is closed over here. In this region, the switch is open. For the cutoff region, the switch is open. The JFET is open. There's no current. All right. Okay. Now, how we perform the analysis is that first of all we assume that the LC circuit is high Q. So it's based on the assumption that LC circuit provides enough flywheel effect or enough energy storage to maintain a perfect sine wave without any distortion, and including the interval when the switch is closed. Okay, so it doesn't matter when the switch is on or off. In the off state, even the sinusoidal trend is maintained. Okay, we don't have much damping due to the R, and LC is a high Q tank circuit, so enough energy is there just to push the output to be a pure sine wave, right? Now, referring to the figure of class C amplifier over here, you see theta C is the conduction angle. VDC is the supply voltage. Alpha VDC is the peak voltage, which is reached, okay, both positive and negative due to the flywheel effects. So it's written over here, theta C is the conduction angle, VDC is defined as the supply voltage, R is the resistance of the switch. Which switch? JFET switch, okay. Alpha VDC is the peak voltage of the sine wave. So let's try to find this alpha, the factor alpha, because this factor is going to come in calculation of the efficiency of this amplifier. And it also, you will see that it affects the power that is delivered at the load, the average AC power delivered at the load. So how we find the alpha is, so the idea is that the input power, which is supplied by the battery over here. So this is the battery source which is supplying the power. Power supplied by the battery must be equal to the sum of the output power dissipated in the load, plus the power dissipated in the switching resistance R. Okay, so you see over here we have the load and we have a switching resistor R over here. So whatever is the power being supplied and ideal conditions, assuming no other loss in the circuit, the power supplied by the battery is VDC into the whatever is the current, I input current. So this is the product of VDC I. VDC I is the power supplied by the battery. Okay, and that is equal to the power lost in the resistor R, and then you have the power loss in the JFET. Okay, power loss in the JFET in the small resistance R. All right. Well, basically this PR is equal to this PR. Okay, I square R. This is the current through the switch. I square times R is the power lost in the switching. Okay, so whatever is the power supplied by the battery should be equal to the power loss dissipated in the resistor and the power dissipated in the switching action. All right. So, so if we consider this conservation of energy, these terms can be given respectively by the average of the battery voltage times the current. So, for example, this alpha VDC square over R is basically this expression is your power, average power dissipated in the load R. Okay, where this 2 comes from is if you consider, for example, the expression alpha VDC plus VDC. Okay, and let's not forget this is a sine, so let's have this sine of theta. Okay, sine theta plus VDC, and you square this out, square divided by R, and the average power, let's see what it comes down to. You see, if it consists of 3 terms, you will have alpha square, alpha VDC square, alpha VD square, whole square divided by 2R. Why 2R? Because if you recall, the average of sine squared theta, is 1 by 2, 1/2. Okay, average of sine squared theta or cosine squared theta is the same. So that's how you are getting this 2 over here, right? This 2 over here. So that's the power. That's the AC power. If you're considering the AC power loss in the resistor, okay, then the other two terms will consist of, for example, VDC square or R. We are not interested in that because that's the DC term. Okay, VDC over R, you will have this term plus alpha VDC square over 2R. Okay, that's the AC power lost. That's the AC power dissipated. So this is the term we are after. And the other term is 0. The third term is 0. Why it's 0? Because you see it will be 2 VDC square alpha times average of sine theta. Average sine theta is 0. So let's not consider that term. Okay, so this term is the power lost in this resistor, right? For the for the JFET, for the energy that is dissipated in the JFET when it's being used as a switch, this term, if you realize, is the current I through the JFET. Isn't that right? Because you see over here at this instant when the switch is on in during this conduction cycle, theta C, we have VDC minus alpha VDC, this voltage, okay, divided by R is the current, this current, so this current is VDC minus alpha VDC over R, and this ratio square, I square R, small resistance R, is your power. So this is the power lost in the switching action. So that's the power supplied. This term is the power supplied by the battery, okay, and which is equal to, you have VDC over here, which is actually VDC multiplied by I, okay, VDC multiplied by I. Okay, then you integrate this to find the power with respect to the conduction angle theta. So this power supplied by the battery, PS, if you consider the average power, then this is equal to the power lost in the load, the average power in the load, plus the average power lost in the switching action. So this is I square. This is I square. You have square over here into R. So power supplied by the battery is the power lost in the resistor load plus the power lost in the switching action. Okay, this is the conservation of energy. So if you rearrange those terms, remember that what we are doing is we are trying to find this parameter alpha, which is the fraction of VDC, how much this flywheel effect is causing the amplitude of the sine to reach, because you remember alpha is the ratio of VDC over here. So alpha VDC is the amplitude of the sine, okay, the sine wave. Now, if you rearrange this term, you do the integration, you can end up in this relationship, okay, and as a result, you carry out the integral and you solve this for alpha. You see that alpha will depend on two parameters over here. Okay, after you carry out the integration and rearrange the terms in this energy balance equation, and you rearrange this term and make alpha the subject of the relation, what you have is alpha expressed in terms of the conduction angle theta C, and you have a ratio of the JFET resistance and the load resistance. In this figure, this alpha is plotted against alpha square. Alpha square is plotted. Alpha square is on the vertical axis, and your conduction angle is on the horizontal axis shown. So okay, so alpha, there are 5 different range of values for R over R. So you have 0.01 for the solid line over here. R over R is 0.05. These are the dotted lines. So what you are looking at is that it looks like that alpha square, which is proportional to the, it is also proportional to the, I would say, the energy dissipated in the load. Isn't that right? The energy dissipated in the load, you see over here, it's proportional to alpha. So alpha square VDC square over 2R. So it's also the energy which is dissipated in the load resistance. So the quantity proportional to the output power in proportional to the output power dissipated in the load is plotted in the figure below for 5 different values of R over R, the ratio of the switch resistance to the load resistance, right? So so what happens is that around 180 degrees you have the maximum for all the 5 different cases. For example, 0.1 is a more practical case where the ratio of small r to capital R is 0.1. And if you consider this curve, for example, you have an efficiency close to 1. Sorry, not the efficiency, the alpha is close to 1, right? So it's like the power is equal to VDC square over R. Over here, if alpha is 1, then you have the power is alpha, it's like VDC square over 2R. So if you are going, and this looks like if you are going to derive this amplifier at 180-degree conduction angle, because if you're going to increase it beyond 180 degrees, you see at 180 degrees this is pi by 2, so the numerator is maximum, right? The numerator is maximum at 2. If you're going to increase this beyond pi, the numerator becomes small, and the physical interpretation is that if the conduction angle exceeds 180 degree, the incursions into the positive loop extracts energy from the tuned circuit, and the power is reduced. Okay, the power is reduced. We don't want that. So note that alpha square and therefore alpha can be greater than unity. Okay, so we have seen this alpha can be greater than unity over here as well, depending on what the ratio of small r or capital R is. So this happens especially when the conduction angle is 180 degrees. Okay, so this is how you find alpha from the energy balance equation, and you see this curve is showing the values of alpha for a range of values of small r by r and with respect to the conduction angle theta. Now calculate the efficiency as a function of theta and small r over r. We know how the trend of alpha is with respect to theta and small r over r. We consider the ratio, that is the power dissipated in the load resistor. So efficiency, we are defining efficiency as the power dissipated load resistor. You see over here, efficiency is given by the output power divided by the power supplied by the battery. So divide by the power supplied by the battery. That's your efficiency. Okay, P out over P in. So that's P in is the supply voltage. So over here, this is VDC into I. Isn't that right? VDC into I, and that is being integrated to find the average power supplied by the battery. Theta is the conduction angle. So, and this I is the current through the JFET switch. So now if you plot this for a various values of small r over capital R, you see this, the efficiency is maximum for varying values of r over r, and it reaches to 80%. For example, this is broken line is for eta. So the maximum efficiency occurs at 90 degrees of operation. Okay, so this is the efficiency, not alpha. So class C efficiency versus conduction angle for y different values. So you see efficiency is maximum around 90 degrees, maximum around 90 degrees. Even if you are going to derive this amplifier for the lower duty cycles or lower conduction angles, you see for a class A amplifier you have a 360-degree conduction with maximum efficiency of 50%. For class AB you have maximum efficiency 78.5%. So for example, for class A, you remember for class A, let's say a common emitter amplifier has an efficiency. So efficiency for class A, if you recall, was around, maximum efficiency was 50%, right? For a class B amplifier, 50%. For class AB or class B amplifier, the maximum efficiency was pi by 4 under maximum signal conditions. Okay, so let's remember that this is under maximum signal condition. This is 78.5%. 78.5%. Then for class C over here, you can see the efficiency power out or power input supplied by the battery for class C amplifier. This maximum, you see, even if the conduction angle is less than 90 degrees, and over here you see for conduction angle less than 90 degrees, if the value is 0.05 or even less, 0.01, you can reach maximum up to, for example, 90%. 90% efficiency. So again, class C amplifiers, and you will see that for class D and E amplifiers, these amplifiers are not used for the audio applications because the output is not linearly proportional to what the input is. But if the target is to achieve the efficiency, for example, in tuned circuit, in RF transmitters, and oscillators, etc., if you're going to use class, if the efficiency is required, then that's where you employ such amplifiers, okay, for high efficiency. So if you rearrange this integral, you have this efficiency in terms of the conduction, okay, in terms of alpha and conduction and the ratio R over R, right? And you can see that for even for lower conduction angles or low duty cycles, varying with very small resistance of very small ratios of switching resistance to the load resistance, you can attain a maximum efficiency of 90%.